Welcome to the Tutor TipVid on section 4, the Bloch Sphere. The Bloch Sphere is absolutely vital you understand the Bloch Sphere, so I tell a little story and hopefully that will help. So we've got the Bloch Sphere and all the ways that we can mathematically, through linear algebra, we can mathematically point to any point on the surface of the Bloch Sphere, and that will tell us the quantum state. Now, let's have a look at the classical Earth. So what I say to my students, I quite often say, get two A4 sheets of paper, run up to the North Pole and stick the one A4 paper to the top and run back down to the South Pole and stick a paper there, an A4 paper, to the ice at the South Pole. Now, that is actually, in all honesty, that's the equivalent of what a classical bit does. It can be on and off. It can only ever be 1 and 0, no other number, no other location, that's it. But let's move over to the quantum bit. Now, that's like covering the entire Earth in A4 pieces of paper, which I call zoo paper, 0 or 1, and there's a reason for that later. I mean, how many A4 papers do you think would cover the globe? Well, I've tried to work it out, and it's roughly 8.2 million. So there are 8.2 million more reference points on quantum Earth than classical Earth. So there's a great start. I might say, just to get back to reality for a second, we can't access every A4 paper, but we can access many, many areas through our microwave bursts. They're getting more and more accurate, and we can locate many, many locations on the Bloch Sphere that we can address, reference, map, just as well as we can map 0 and 1 for the classical state. Now, and for the Earth, the classical Earth, you know, I'm just going to take the North Pole. There's a zoo paper for every single location, whether it's classical or quantum. Now, the zoo papers, there's only 2 for classical. One's up, one's down, one's 0, one's 1. There's not much going on here. So there are only 3 fields, and I'm going to call them the ID and the latitude and longitude. And of course, it doesn't make sense really in the classical world. But if we take a look at the quantum world, we can see that latitude and longitude, just like we use it to actually reference points on the globe, we can use it to reference points on the Bloch Sphere. And the latitude and longitude, just for those of you who know, are the complex amplitudes. They're basically saying, what's the chance that the particle is going to collapse to that particular point on the face of the Earth, on the face of the Bloch Sphere. So there's the one thing, this is very, very important. This basically is the most important thing to remember. If the A4 zoo paper, the A4 piece of paper is in the northern hemisphere, it has a greater probability of being a 0. Because remember, when you collapse or measure a cubit, it goes to 1 or 0. That's just the way it is. And if the zoo paper is in the southern hemisphere, then it's got a greater probability of going to 1. You mightn't think that is that important, but I'll prove to you that it is. Okay, here's a little joke I do to my students. An alien comes to Earth, floats over Earth and says, I'm thinking of a number, a 6-digit long number. So that's basically just 1 short of 1 million. And I want you to get it right in one go, or I'll blow up your silly Earth. Okay, the students like this. Now, if we only had a classical computer, and let's say the only number is 101001, you can only choose 0 or 1. The classical computer, and I say it's like you got a photocopy of the Earth, the classical Earth, and then you use it as an abacus. And of course, my younger students have no idea what an abacus is, but basically that's how limited we are. We take a photocopy of the classical Earth, they're not linking to each other, and then you have to go through each one and find out, using a bit of logic code, whether it's a 0 or 1. We're going to get blown up. No, we're not going to get blown up, because the quantum computer can guess it in one attempt, because every quantum Earth, in addition to having 8.2 trillion places we can map, it also can relate to other Earths, quantum entanglement. So you get the quantum Earth as a qubit, and you can entangle it with other qubits, and it just means you've got, 8.2 trillion times 8.2 trillion computations you can do in one go. I might add, if we have 300 quantum Earths, 300 qubits, we can do calculations totaling the same as every atom in the observable universe in one go. So the Earth is safe thanks to quantum computing. But quantum physics is weird. Did you know that you can't look at the results? What would you say if I said to you, I've got the best calculator ever? It's unbelievable. It can do every single calculation you've ever thought of. But the problem is, when I turn it around to you to show you the answer, it's 1 or 0. Well, you'd say, well, what the hell is the point? And a quantum computer, you cannot ever know the answer, because the answer is a collection of superpositions. And as soon as you look at them, we know it just collapses to 1 or 0 with equal probability if you're on the equator at the quantum Earth. A quantum computer cannot copy and paste, cloning theorem, and the qubit can only work on a computation for a few milliseconds. It is very, very strange. But what I'll do now is I will tell you how we can get around the measurement problem and make wonderful calculations. And we actually use probability. Quantum computers can never give you an exact answer. They can give you what the answer probably is. And you probably think now, well, that's not what I want the exact answer. But you would actually be surprised how often in mathematics and the world of commerce, that probability does the really, really big calculations. It's like me saying to you, can you tell me what's the chances of me throwing a 6 with a normal 1 die? You might say to me, well, it's 1 in 6. Now I can work that out because I can work it out mathematically. So I can say the number of correct combinations that meet the parameter over the total possible combinations. So that's 1/6. Or I could throw the dice 1,000,000 times and see what the chances are, and you'd find it'd be amazingly close to 1 in 6. Okay, let me now tell you how a quantum computer works out huge calculations. Okay, so let me explain how it all works. So we'll do our quantum Earth. So here we are here, and it has the whole Earth, surface of the Earth is covered in what I call these zoo papers. And remember, a zoo paper just has 3 fields, which we call an ideal, an ID, and a latitude and longitude. Okay, so like I was saying before, we can't measure the zoo paper or the quantum state. We can't measure it. We can't know the latitude and longitude of any point. We can't know the complex amplitudes of any quantum state on the Bloch sphere. So isn't that a shame? Because when you think about all of the wonderful calculations we can do, because a qubit and a quantum gate basically moves around the qubit, changes the quantum state of the qubit. So it starts off in the North Pole, but then the quantum gates move it, and all these zoo papers aren't just 1 and 0. They have complex and imaginary numbers. So they could be the square root of I to the pi theta divided by the square root of 13 over, et cetera, et cetera. And when you multiply them together, you're getting these absolutely exponential computations, but you can't look at them. But what you can do, and this is where, remember I said to you, so here's the equator, and that's where it's a qubits in superposition, so it's an equal chance. But remember I told you, if it's in the northern hemisphere, it has a greater chance of being 0. And likewise, it's a greater chance of being 1 if the zoo paper or the coordinates of the superposition happen to be in the southern hemisphere. And I told you then that that was really important, and it is, because this is what we do. We then run the algorithm. An algorithm is just all of the quantum gates in total, and all of the complex multiplications. The algorithm is just all of, a collection of them together. So it's X gate, NOT gates, Hadamard gates. At the end of it, it's just one algorithm. And we run the algorithm millions of times. The more, the merrier. And so there's a billion times we can run it if needs be. And remember, when we measure the qubit, all we get is a 0 or 1. That's why it's called a zoo paper, 0 or 1. But what we get if we run it a billion times, we might get 700,000. I'm not going to do this properly, but 700,000 times it's a 0, and then 9. Oh, you know what I'm saying? They both have to total up to. I've messed that up, but they have to total up to a billion. It equals 1, and what that gives us is the ID of the zoo paper. That percentage there between the 0s and 1s will bring us back to a zoo paper. And if we get back to that paper, or in the real world, if we get back to what the probability, which quantum state equals the probability that we've ended up with, that ID will then be the answer. And that ID is a very complex, is worked out from the latitude and longitude. But isn't that amazing? And that's how quantum computing is done. I hope this has helped you visualize everything, and I look forward to seeing you in the next session. Thank you very much once again.